So in this lab, we are intending to calculate the sine function using Chordate algorithm, and we're going to implement the Chordate algorithm in Vivado HLS. And then we're going to export the Vivado HLS IP that we generated to Vivado and create a design block. And then using that, we are going to integrate the IP with ARM processor of Zinc using the Vivado SDK. So the basic milestone that we're going to go through are as following. First, we're going to implement algorithm in HLS. Then we're going to export the IP from HLS. Then we're going to add it in Vivado, build a block design, export to SDK, and using ARM processor in SDK, we're going to try to read and write from the IP. So first, let us make the HLS project. Just to create a new project. This would be the project name. There's no real requirement to specify the top function right now. You can do it later when you're preparing your code for synthesis. Same goes for test bench files. We can do it later. It is important for us to specify the board that we are going to use. The institute has provided me with Zybo Z10 board. Since I'm selecting the Zybo Z710 board, you can select the respective board that you have. The basic algorithm, the basic coding, you can learn the basic coding algorithm and how it works from the link that we provided over here. In chapter 3, there is a brief explanation of coding algorithm, and there is an in-depth explanation of coding algorithm and the math behind it and how it works. And it has also provided you with the C code that you can C code without any optimization that you can use to implement it in HLS. First, let me just specify the design files and the test bench. It's important for you to specify whether you're writing it in C or CPP. I'm writing it in C++. Thus, using the .cpp. I'm sorry for the phone notification that is turned up. I muted it now. I apologize. Now we are adding the test bench file, which should be the same as the design file. The code is provided you in the handout. Right now I'm copying the code. This is the test bench code. This one. The design code. By the way, we have provided you with two types of code, one optimized and one unoptimized. I'm doing the synthesis and the test. I'm going to be only explaining the optimized code, as we have only added certain things or changed certain things from the unoptimized code. But it is highly recommended that you use both optimized as well as unoptimized code, synthesize both, and then see the difference in the latency that you're getting, difference in the hardware utilization that you're getting. There should be a massive difference in after synthesis, and I think visualization of that would be highly helpful for understanding how Vivado HLS works and how these pragmas basically works. So in this segment, we will try to visualize how the coding algorithm works when we calculate the sine function. So the best way to think of coding algorithm is that it is a binary search for vectors. Basically, this is the target vector that we need to reach, which has angle theta with the x-axis, the positive x-axis basically. So we need to reach this vector, and when we reach this vector, the x and the y coordinates will give us cos theta and sine theta respectively. So the best way to reach best way to start is through a vector that we know. So we know a zero vector. So we know an x-axis. So we know the x-axis, and we can start at angle theta. We know the values of cos theta and sine theta of this vector, and we'll start from here. Next thing that we'll do is we will divide these two axes, this area, in two parts. We'll divide it by using this vector, by rotating the initial x-axis vector by 45 degrees, because this is 90 degrees, so we'll divide it in half by using 45 degrees. Now we need to see in which direction our target vector, which is the green vector over here, lies. So the target vector lies in this area. So we will make sure that so we will rotate. We will again divide this area in half. The best way to divide is by rotating this red line, this vector by 45 by 2 degrees. 45 by 2 is 22.5. Rotated by 22.5 degrees. So let us assume that after rotating this vector by 22.5 degree, it will come over here. And now we will again see where our target vector lies. The target vector lies in this area, and we will again divide this area in two parts. So best way to do this is rotate this vector again, but this time we will rotate it clockwise. We'll rotate it clockwise by 42 by 2 square, or 42 by 4. We'll rotate it by 42 by 4 in anti-clockwise direction, and we'll keep on doing that until we get a precise we get as close as possible to the green vector. So the more divisions that we do and the more iterations of the binary search that we do, we get more closer to our target vector. But on the other hand, the more iterations that we perform, it will take a lot more time for calculating the result. So this is the basic this is the visual aid of how we calculate the sine theta by using the Corbett algorithm. But the important thing is we need to learn what are the optimization that we have done. The first most visual optimization we have done is the APFix one. We have included an APFix library. Basically, what this library allows us, sorry for the minute. Basically, what this what this library allows us to do is, this library helps us to define define a data type such as float or double to our own comfort. So we know that float is of 32 bits and the double is of 64 bits, but we are handling data. We don't need that much bits for representing our data. As you can see here, we're using 45 and 0895, and we are calculating the theta of 60 degrees only. So we don't need 32 bits to represent our data, and it would be really hard. It would be really heavy on the hardware. Hence, we defined our own data type, which is of 16 bits, and with 8-bit integer part and 8-bit the decimal part. So we have defined it over here. And then we're using this, and we named the data type as fixed, and we're using this data type for calculation in the actual algorithm. But as you can see here, we are using float over here and over here. We're returning float, and we are taking parameter in float. The basic reason behind this is the communication between PS and PL part in the Zinc board happens using AXI protocol. And AXI protocol in AXI protocol, data transfer happens in 32 bits. But we need to provide, as you can see here, we're using fixed, and we need to provide the data in 16 bits. So there are two ways to handle that. The first way is to make sure that we're converting a double in SD, converting our float in SDK to a fixed format, which we have defined over here, and then passing that data to the IP, or we can add a converter of 32-bit to fixed and fixed to 32-bit in our IP itself. So I choose the latter one, where I'm taking the data in a float form, which is of 32 bits, then converting that float data into fixed over here in this line, as you can see. And I'm doing the same at the end, just the vice versa. I'm returning the data in float form, but I've calculated the data in fixed. So I'm going to convert current sine theta to float using the inbuilt function that is provided in the APFix. And then I'm going to return the data f answer, which is the final answer, and I've done the calculation of sine theta. By the way, you can also calculate sine theta as well as cosine theta by using current cos. You can just here add current cos, and it will provide you with the cos value. But for the sake of this lab, we only want to give sine value. So the next optimization that we are doing is Pragma HLS unroll. So first, let us understand what Pragma HLS interface SAXI Lite port is doing. Basically, it defines for the it defines the IP that we are communicating using AXI 4 protocol, and we are defining the ports through which it is communicating. So it is gonna receive data from theta from port theta, and it is going to give data from port return. We are defining that with the help of these two pragmas, and we are also using Pragma HLS Unroll. So Pragma HLS Unroll, there's a basic. You can learn more about optimization. By the way, you can learn more about optimization over here. As you can see that in FIR filters, FIR filter chapter in the book that is provided over here, you can see that there is lot of optimization algorithms, optimization ideas, like using loop fission, then loop unrolling. We have basically used loop unrolling over here, where we unroll the loop. To give you a better example, just yeah. As you know, as you can see over in the first for loop, that we are iterating 10 times. From as you can see over here, we are iterating 10 times, and in each iteration we are performing one operation. But over here, we are iterating 5 times, and we are in each iteration we are performing two operations. So this is loop unrolling. We have unrolled the loop by a factor of 2. We can define, by the way, we can define the factor which we are unrolling in the HLS as well. But I have not done so. I let the compiler handle that. But you can we can also divide the we can also unroll this by factor of 3 by just doing this. Behind I plus 3 over here. Then I'm adding another uh, operation over here. Just like this. Here I unroll the loop by a factor of 3. This is the basic idea behind loop unrolling, and with an in-depth analysis of how the compiler works and how you can visualize, you can deduce that this helps the hardware this helps in the performance of the hardware. Similarly, we can do loop fission, where we sometimes loop fission is basically very counterintuitive. We divide the loop in two parts. We divide the loop into smaller loops, and the basic computation is way smaller. But that we have not used loop fission in this code. So yeah, we are only using HS unrolling, and we have not decided the factor here. We just add as factor equal to 2. And this would work. But I let the compiler handle that. So yeah, this is the basic optimization that we have performed, and the b- in the back code, the basic code, you can find the code in the main in the link that we provided of the book. You can find the code over there. Let's just save this and run this code to check whether this is working or not. I'm providing the theta over here, and getting sine theta. Remember, we are providing in float form, as you can see over here. As you can see over here. So for this is C simulation. We are using the test bench to verify whether the function that we have made is correct or not. So this is this okay. And see what we're getting. Just give me some time. Yep. Here's the final answer, that sine theta is equal to 0.859375, and the theta value is 60, and 60 is in degree. You need to 60 is in degree. Let us just verify whether the answer is correct or not. Just going to write 60 0.8660. So this is acceptable, as we have the precision. As you can see, that the precision is very low. That we are getting 859, but here it is getting us 866. And we can improve the precision of the result by adding more data to the codic phase. So the more data that we add to the codic phase, and the more times we iterate it over, we iterate and do binary search more, the, the more precise our result will get. Just adding the data over here will improve the data, improve the values that we are getting. But on the other hand, we it will reduce the time. It will increase the time for calculating a single result. So as you can see here that the basic algorithm is working. Let us now synthesize it to see the hardware utilization and the latency that we are getting. So to synthesize first, go to project settings as we need to define the top function for which we need to synthesize. So here we will write the top function, and the top function is codic. As you can see over here, top function is codic, or you can just browse for it as well. See, it is giving us as codic over here. So just press it as okay, and yep. So we have. So now we can run C into this. Let's see if we are facing any errors. So here's the synthesis report of the top function. We are getting a latency of 27 and hardware utilization. You can see the hardware utilization over here, and from the total number of LUTs that we are consuming, the percentage that we are consuming is written over here. 2%, 1%, 10% is pretty low utilization, which is better. Yes, the synthesis is complete, and now we will export the IP. To export the IP, we just need to export the RTL, and then IP catalog is perfect. And, you don't need to do anything. And, yeah, you just export the IP catalog. Now remember, don't close the HLS. Don't close the Vivado HLS over here because there are certain paths that are important for us to tell the Vivado that where our IP is located. So don't close this. So while it is opening, let us just okay. So you finished exporting RTLs, IP is created, and yep. Let's open Vivado to implement the block design, to create a block design. My bad. By the way, I don't know if I told you already, but to learn more about the optimization, you can refer to the FIR response filters. I read this part, and it is very helpful in to give you knowledge of how you can optimize your code based on the hardware that you're using. So it is important that you keep the hardware in mind, and through trial and error, you can figure out what's the best optimization that you can do. As you can see over here, here's the unroll factor. Yeah, there's the command. So yeah, there's a lot. Let's create a new project. Let's just name the project as. There's no need to specify the sources, so you can check this box. It is important to specify the board. We're using Zybo Z710. Select that board only. Okay. So now we need to create a block design. So let's just create. Let's just click on create block design. Design. So it's first add the process zinc IP, and then we will run block automation over here to connect. Let's press on OK. And now comes the crucial part. First, let us just see whether the IP is located over here or not. Coding. This is not the IP that we created. You need to remember that the name of the IP would be the name of your top function. So let's just open the Vivado HLS to see what's the name of our top function. The name of our top function is codec, and we cannot find codec over. Um, we cannot find codec anywhere. This is not the. This is the pre. This is the inbuilt implementation of codec. We are not using this, and this is my own previous implementation of codec. So this is not the IP that we have just created. And basically, why we are not seeing that IP is because we have not specified the path where which the IP is located to the Vivado. Let's just do that. And for that, these paths. No, these paths that we have provided over here are important. We need these paths to for the Vivado needs these paths to locate where the IP is. So this will go to Vivado, and now go to settings. There are two places where we need to update the path. First, an IP repository. You can add the path over here. Just click on plus, and just you can either go to Vivado HLS and copy paste this one here, label this part of the path, or you can just search it. You can just browse for the IP in the Vivado itself. So I'll show you how to browse it, and then in the second one I'll show you how to copy paste the IP, path. So as you can see that this is the HLS project that we have created. So let's open this project. The IP would be located in solution 1, as everything that we have synthesized will be all the VHDL or all the Verilog codes will be over here. And then IMPL, here's the IP. So just select this, and this is where the IP is located. Okay. So we have added the IP to IP repositories. Then we're going to do the same in IP defaults. I'm gonna add. If you added, by the way, if you added the IP in repository, the default one would be the default one that I have given here would be the same as the one you have just added in the IP repository. Yes, you can just click on OK. Yeah, you have added both the location of the IP, and then you can move this as apply. Yes, it is very necessary that you apply it. Yeah. And then click on OK. So now if you check, you should see your IP position. Here it is. The top function name was codec, and we are able to see the IP over here. Just press on it, and then it will automatically get added in the block design. So now we need to run connection automation. This will connect the IP using the very different using various peripherals. Next, let's just regenerate layout so that it's way cleaner. Now it's important to validate the design. Let's just validate it to find are there any errors or not. There are some critical warnings which can be ignored. I think the validation of the design is complete. Let's just after validation, you need to make sure that you generate output product. You can go. You need to go to sources, then right click on the design and generate output product. Now from this point, this will take some time because after this we will add the VHDL wrapper, and then we're gonna run synthesis, and then we're gonna generate bit stream, and after that we will export the block design that we have created to SDK. So yeah, this will take some time. So I was facing some problems in Vivado, and you know, so let's do this again. So we were generating output product. After clicking this, it will generate the output product, and it should look something like this. And after that, you can create HTML wrapper. Let the Vivado handle it. It is updating. After the HTML wrapper is updated, you should run synthesis, or you can just click on generate with stream, and it will automatically launch synthesis and implement it. Yeah. So this will take some time. It will show you the exact hardware implementation, the hardware utilization of the board, uh, the power consumption, all the reports. Okay, so the bitstream is generated and the synthesis is complete. Let's just open the implemented design. Here you can see the hardware utilization. The bitstream generation is completed, and now we can export the block design to the SDK. So just click on export hardware from files. After doing that, you need to include bitstream as we are doing the computation in PL part in hardware. So it is important to include the bitstream. So yeah, after the bitstream is done, just launch the SDK, and you will handle the code in SDK in the next video.